Good morning to all of you. Here I am continuing my discussion on quantum mechanics part 2. So this is Naren Sharma. So from First Grade College, Vattur, Government First Grade College, Vattur. I am continuing my discussion on quantum mechanics part 2. And today's topic that I am discussing is about a hydrogen atom. So this is for BSc Physics course, 6th semester, paper 8. So let us see the objectives of this particular session. We have been discussing the applications of Schrodinger's equations on various physical systems. So first we applied Schrodinger's equation to a particle in a one-dimensional box. Then we also discussed the behavior of a particle in a three-dimensional box. Then we applied Schrodinger's equation to a one-dimensional linear harmonic oscillator. In a similar way, we are continuing our discussion and we want to apply Schrodinger's equation to the hydrogen atom. So our major aim of this particular session is to apply Schrodinger's equation to the hydrogen atom. So this is slightly a complicated thing for the degree level. We are not discussing the complete mathematics here. So we are discussing the three important equations that arise because of the application of the Schrodinger's equation to the hydrogen atom. We are not going to obtain the complete solutions, as I told. So these mathematics involved are slightly of a higher level compared to BSc course. So therefore, what shall we try to do is we shall try to apply Schrodinger's equation, and we shall see what are the three different equations that we are going to get. Automatically, if we are going to solve the equations, of course we are not going to solve the equation. We are going to end up with two different things. The first thing is the expression for the energy eigenvalues of hydrogen atom. The expression for energy eigenvalues of the hydrogen atom is a well-known thing. The expression for energy eigenvalue of hydrogen atom can be derived very easily using Bohr's theory of hydrogen atom. But here we shall try to mention the expression for the energy eigenvalue, the same old expression that we get using Bohr's theory, but by making use of Schrodinger's equation to the hydrogen atom. Also, it is possible to write the expression for the wave function. Particularly as per the syllabus, I would like to mention the ground state wave function for the hydrogen atom. So these are the three important objectives of my discussion. So applying Schrodinger's equation, and therefore in order to obtain the energy eigenvalues of hydrogen atom as well as the ground state wave function, only the ground state wave function of the hydrogen atom. So these are the objectives of this particular session. This is the fourth application. That's why I have written it as 4. We are applying Schrodinger's equation to the hydrogen atom. So please remember, in the case of hydrogen atom, so there is a single proton that is the nucleus, around which there is a single electron which will be revolving around the nucleus in a circular orbit. So as per classical theory or Newtonian mechanics, the force that actually binds the positive proton and the negative electron is the electrostatic force of attraction. And because of this electrostatic force of attraction, our hydrogen atom possesses a potential energy. And the potential energy of the electron or potential energy of the entire hydrogen atom can be written in this particular fashion. So it is the same old expression for the potential energy between two point charged particles. So potential energy is a function of the distance between the nucleus and the proton and the electron. Because in the case of hydrogen atom, the nucleus is nothing but a proton. So therefore, that the distance we write it as r. So the potential energy V of r is now given by minus c squared divided by 4 pi epsilon naught r. So therefore, we can conclude that the potential energy is a function of only the distance between the nucleus and the electron. So this potential energy is independent of any other factor. So because of this particular dependency of the potential energy on exclusively the distance between the electron and the nucleus, so the entire problem of hydrogen atom can be solved using Schrodinger's equation, not in terms of Cartesian coordinates XYZ, but in terms of another set of coordinates. We call them as spherical polar coordinates. Our hydrogen atom is an example for spherically symmetric case. Why it is spherically symmetric? It is all because the potential that is defined by this equation 1 is spherically symmetric. So what the potential is spherically symmetric, it is all because the potential energy between of the system depends only on the distance. It does not depend any other factors. It does not depend on any other factors. So therefore, the potential hydrogen atom potential function of the electron around the nucleus possesses spherical symmetry. So because of which this entire problem of hydrogen atom can be solved in terms of spherical polar coordinates, which are denoted by r, theta, phi, rather than the Cartesian coordinates x, y, z. It's also possible to solve the hydrogen atom case in terms of x, y, z, but the equations become cumbersome and they are too difficult to solve. So therefore, rather than going to Cartesian coordinate system, we are making use of the spherical symmetry of the potential of the electron around the nucleus, and therefore we are going to solve the equation in terms of spherical polar coordinates r, theta, phi. So as these coordinates are orthogonal to each other, so it is possible to express the wave function of the hydrogen atom as a product of separate function. So the three coordinates are theta, phi. Let us proceed further. Let me go to the next slide. So before I come to the equation, Schrödinger's equation in spherical polar coordinate, let me mention the general three-dimensional Schrödinger's time independent equation. So the general three-dimensional Schrödinger's time independent equation is given by dou square psi divided by dou x square plus dou square psi divided by dou y square plus dou square psi divided by dou z square plus 2m by h cross square e minus v times psi is equal to 0. This is what? So the expression for the Schrödinger's equation in terms of Cartesian coordinates x, y, z. As I have already told, solving this particular equation in terms of Cartesian coordinate system for a spherical system like hydrogen atom is difficult. So therefore, rather than Cartesian coordinates, we go for the spherical polar coordinates. And the spherical polar coordinates are theta. So they are nothing but r, theta, and phi. Now, there is a little bit of mathematics involved here, and we are avoiding this mathematics. This entire equation can actually be expressed in terms of r, theta, phi. If we are able to express Schrödinger's equation in terms of r, theta, phi, we are going to end up with little lengthy and cumbersome equation. And this equation is represented by 2. And therefore, equation 2 actually represents the same old Schrödinger's equation in 3 dimensions, but in terms of spherical polar coordinates r, theta, phi. So I'm going to read out this equation. So in terms of r, theta, and phi, the Schrödinger's equation is given by 1 by r square dou by dou r of r square dou psi by dou r plus 1 by r square sin theta dou by dou theta of sin theta into dou psi by dou theta plus 1 by r square sin square theta dou square psi divided by dou phi square plus 2m by h cross square e minus v times psi is equal to 0. So this is what the thing that we are going to get once we are expressing the equation in terms of spherical polar coordinates. We need not have to worry about the derivation or reduction of this equation into this equation. So the mathematics, we are not interested here. But anyhow, in terms of spherical polar coordinates, the Schrödinger equation is given by equation 2. As I mentioned in the previous slide, so the expression for the hydrogen atom is given by minus e squared divided by 4 by epsilon r. So therefore, in the equation 2, I can replace the potential energy. And once we use the potential energy expression, I'm going to get the same expression. Of course, in the place of v, we are going to get minus e squared divided by 4 by epsilon r. So totally, this term becomes 2m by h cross square times e plus e squared divided by 4 by epsilon r into psi is equal to 0. So this equation 3 represents Schrödinger's equation applied to hydrogen atom in terms of spherical polar coordinates r, theta, and phi. Now, we need to solve this particular equation. Once we are able to solve this equation, then we are going to get the eigenfunctions of hydrogen atom as well as energy eigenvalues of the hydrogen atom. That is what our the next thing we need to do. The solution of this equation can be done by the method of separation of variables. The separation of variables is a method that we have used in the case of particle in a 3-dimensional box. The same method we are following here also. As I mentioned in the previous slide, so r, theta, phi, they are mutually perpendicular coordinates. So therefore, this entire wave function psi, which comes in this equation 3. So the wave function r, theta, phi can actually be written as product of 3 separate functions. So wave function psi, which is a function of r coordinate, theta coordinate, and phi coordinate, can be written as the product of three separate functions. So the first function would be a function of only the r coordinate. The second function would be a function of only the theta coordinate, and the third function is also a function, pure function of the third coordinate phi. So therefore, this entire wave function psi r theta phi can be separated as three different functions, each one being dependent only on one independent variable. For example, I have written here capital R. Capital R is a function of the radial coordinate r, and this is also theta, capital theta. Capital theta is a function of the angular coordinate theta, and phi, capital phi is the function of the third coordinate small letter phi. So therefore, equation 4 is what we call it as the method of separation of variables. We are using this method of separation of variables in order to solve this equation 3. So we are going to insert this equation 3. Sorry, we are going to use this equation 4 in equation 3. So we are going to replace this psi by capital R, capital theta, and the capital phi. Once we do that, that means if we substitute equation 4 in equation 3, and what we are going to do is in the previous equation, let me come back here. So what we are going to do is we are going to insert this equation 4 psi as capital R, capital theta, and capital phi. And we are inserting, and then what we are doing is we are dividing the entire equation. So dividing the entire equation by r theta phi. That means psi itself. So the equation 4 must be inserted by r theta phi, and r theta phi also should be divided. Should be the divided term. So then if we do the rearrangement, then we are going to get this equation. So sine square theta divided by r, dou by dou r of r square dou r by dou r, sine theta divided by theta, capital theta, dou by dou theta of sine theta by dou theta by dou theta. So 8 pi square m r square sine square theta divided by h square, e plus e, capital E plus e square divided by 4 pi epsilon naught r. So students should not get confused here. Capital E is the energy of the hydrogen atom. Small e is the charge of the electron. And also this is a symbol for capital theta, which is a function of the coordinate small theta. Similarly, capital R is a function of small r. And on the right side, we have a term minus 1 by phi, capital phi, dou square capital phi divided by dou phi square. So capital phi is another function, which is a pure function of phi. So therefore, if we do this mathematics, then we are going to end up with this equation 5. So we can see this equation here. If we observe this equation 5, left side, we have so many terms, we have many number of terms, and all these number of terms are functions of small r and small theta. So left side of the equation 5 is consisting of terms, and those terms are functions of two coordinates, small r and small theta, small r and small theta. But on the right side, we have something like a function capital phi, and we know that function capital phi is a function of only small phi, the angular coordinate small phi. So therefore, left side we have terms consisting of r and theta, and right side we have a function that is a function of only the coordinate phi. So therefore, this is possible only when the left side term and the right side term. Left side term is a function of r and theta, right side term is a function of phi only, and they are equal. Actually, as per this equation 5, both the terms are equal, and this is possible only when each of these terms, the left hand side term and the right hand side term, must be equal to a constant. So what I want to say is, equation 5, whatever I have written equals, each term in the left side and the term on the right side, they must be equal to a constant. Then only equation 5 is satisfied. Otherwise, equation 5 cannot be satisfied. So we are calling that constant as the ml square. So therefore, I'm substituting here equation 5 is equal to ml square. If I do that, we are going to get one equation, minus 1 by 5 dou square phi divided by dou phi square is equal to ml square. I have already told ml is some constant. And if we simplify this equation, then we are going to get one equation, and that equation is what we call it as azimuthal equation. So the azimuthal equation is d square phi divided by d phi square plus ml square phi is equal to 0. So this is the capital phi, which is the function, and small phi, denominator we have small phi, that is the variable, azimuthal variable. This equation is called azimuthal equation because so the coordinate small phi is what we call it as azimuthal coordinate. So therefore, so whatever the three terms we had, whatever three different functions we had, we are able to obtain differential equation for one particular term, capital phi. So we have the differential equation of this form, d square phi divided by d phi square plus ml square plus phi is equal to 0, where ml so is right now is called as a constant. So that is called equation 6, and equation 6 is what we call it as azimuthal equation. So this is a simple linear second order differential equation, and solution of this equation is actually given by phi, capital phi is equal to a times a is some constant exponential e power I ml phi. So this is a standard solution of this equation 6. So therefore, in order that the above equation to be single value, I'm not discussing all the things in detail. This is something like equation 7. The solution 7 actually represents a periodic function. So if this is a periodic function, then actually there's a general solution of this equation such that so phi actually becomes multiple value, and we want to avoid multiple valued functions here. So therefore, we expect this capital phi, the function capital phi, to be single value. And if that is possible, only when, so the possible values of ML are either 0 or negative or positive integers. So what I want to say is, so we should need to put a restriction on the value of ML here. If you put a restriction on the value of ML here, then this wave function part, capital phi, becomes single value. That is possible only when ML can take the possible set of values 0, either 0 or plus or minus 1 or plus or minus 2 or plus or minus 3, etc. etc. Once the value of this constant ML take either 0 or plus or minus 1 or plus or minus 2, etc. 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 then this solution becomes a single value, and the wave function must be single valued as per our description. So therefore, so this constant, what we are calling it as a constant, actually it is what we call it as magnetic orbital quantum number. Okay, so students should be aware of this particular quantum number because probably they might have studied this one in the case of Bohr's theory or the extension of the Bohr's theory, whatever it is. So therefore, the constant that ML we introduced in this equation 6 called as azimuthal equation, that constant cannot take continuous set of values. It can take only some discrete set of values decided by 0 or plus or minus 1 or plus or minus 2, etc. 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 And therefore that constant ML is what we call it as a magnetic orbital quantum number. So therefore we can conclude that the azimuthal equation of the hydrogen atom, equation 6, actually introduces one quantum number, and that quantum number is what we call it as magnetic orbital quantum number, and that is what we call it as M subscript L, and M subscript L is what we call it as magnetic orbital quantum number. It is one of the important quantum numbers that are associated with the hydrogen atom. I'm not going to discuss all set of quantum numbers associated with the hydrogen atom, but anyhow, I'm going to show that there are two more important quantum numbers associated with the hydrogen atom. So right now I can say that one of the important quantum number associated with the hydrogen atom, which arises all because of the azimuthal equation 6, is what we call it as magnetic orbital quantum number. The symbol for magnetic orbital quantum number is M subscript L. So this is what one quantum number. So we have come to know about. So in the case of hydrogen atom. Now we did this partially. So we equated equation 5 into ml square. Not only that, our minus 1 by 5 times rho square phi divided by dou phi square is equal to ml square. On the left side, we have three different terms which are nothing but functions of r and theta, small r and small r theta. So therefore, LHS of this equation 5 must also be equal to ml square, because if the right side is equal to ml square, left side of the equation 5 must also be equal to ml square. So that is what we are doing in the next step. So therefore, what we are doing is When we substitute ml square in the RHS of the equation 5, this is equation 5. In the equation 5, so we are equating the left sided term. These three different terms is equal to ml square, and we are rearranging. So, and after rearranging, so we are dividing the entire equation by sine square theta and rearranging once again. And therefore, what we are going to get is 1 by r d by dr of r square plus dr by dr plus 8 pi square mr squared by h square times e plus e square divided by 4 pi epsilon naught r. That should be equal to ml square. This ml square comes because we have inserted that constant, and we are dividing the entire equation by sine square theta. So therefore, we are going to get on the right side ml square by sine square theta minus 1 by theta, capital theta, sine theta, d by d theta of sine theta, d theta by d theta. So this is what equation 8. What we are doing here is the equation that we wrote here, we separated this equation into first one separate equation in terms of theta, and we are continuing our method of separation. And in order to continue the separation, so what we have done is we separated r term onto the left side and the theta term onto the left side. That means in equation 8, left side, the two terms are functions of only the r coordinate, small r, and right side is a function of only the coordinate theta, small theta. So therefore, again we have separated the two equations here. So left side, again in equation 8, left side is a pure function of r, small r, right side is a pure function of theta. So left side a pure function of r and right side a pure function of theta, and both of them are equal as per equation 8, and that is possible only when each of these two terms on the left side and the right side, again they are equal to some other constant. So therefore, so that constant right now, for the sake of completeness, we are taking it as L into L plus 1. We are not writing something like some single term, but instead of single term, so we are writing that constant as L into L plus 1, because L is one more quantum number associated with the hydrogen atom, and that's why that constant, we are not writing it simply L, it is actually L into L plus 1. So therefore, we are equating equation 8 to some constant. That constant, so for the sake of completeness, we are taking it as L into L plus 1. So therefore, once we substitute and again if we simplify, then we are going to get ml square by sine square theta minus 1 by theta sine theta d by d theta sine theta d theta by d theta must be equal to L into L plus 1. And we are going to get another equation 1 by r d by dr of r square dr by dr plus 8 pi square m square by h square into e plus e square divided by 4 pi epsilon naught r is equal to L into L plus 1. So equation 8 we have equated to L into L plus 1, and therefore we are getting two different equations. One is an equation in terms of theta, equation 9. The second equation is the equation so in terms of small r, and that is equation 10. And whatever the constant that we were calling L into L plus 1, actually L has a physical meaning, and L is what we call it as orbital quantum number. So far we call it as constant, but L has a meaning. It is just like your magnetic orbital quantum number. L is also another number, another quantum number, and that quantum number we call it as orbital quantum number. So orbital quantum number is denoted by small l, and the possible values of small l are either 0, 1, 2, 3, etc., etc. So just like ML was restricted to take set of values 0 plus or minus 1 plus or minus 2, etc., etc., etc. So even L is also quantized. That's why they are calling it as quantum number. It is called orbital quantum number because it actually introduces a concept called orbitals. So the possible values of L are 0, 1, 2, 3. So L can take 0 also, L can take 1 also, 2 also, 3 also. L is equal to 0 state is actually called as the S state. L is equal to 1 is what we call it as a P state. L is equal to 2 is called D state. L is equal to 3 is called a D state, or they are also called SPDF orbitals, as students might know this. Now here, so this equation 10, what we call it as radial equation. So this equation 10 is what we call it as radial equation. So this is called radial equation because this equation is purely a function of the radial coordinate r. That's why equation 10 is what we call it as radial coordinate. Basically, mathematically, this is a standard differential equation, and it is possible to solve. I'm not going to solve this equation at all. Right now, directly, I would like to say that the solution of this equation 10, the radial equation, is what we call it as associate Laguerre polynomials. So capital R N L, solution of this particular equation, so is what we call it as associate Laguerre polynomials. They are actually a set of polynomials, so which are called as associate Laguerre polynomials. So therefore, just I would like to mention that. So the solution of this equation 10 is what we call it as associate Laguerre polynomials, and the solutions are so denoted by R subscript NL. They are written R subscript NL. It is because these Laguerre polynomials, they are dependent on L, orbital quantum number, and another quantum number N is what we call it as principal quantum number, that I'm going to mention little later. So therefore, associate Laguerre polynomials are given by RNL, and RNL is nothing but the solution of this particular equation 10, radial equation. And there's one more important thing that we are not deriving, but I'm mentioning directly. The radial equation can only be solved when E is positive or has one of the negative values of En. So this equation has a solutions only when E is positive. E is positive is what we call it as unbound state. We're not interested because hydrogen atom is an example for bound state. So therefore, for a bound state, E must be negative. E not only must be negative, and the possible values of E so are actually given by this expression, equation 11. Of course, we are not deriving this equation, but anyhow, directly I'm mentioning that the solution of this equation 10, radial equation, is possible. We can write the solution only when E is actually given by negative set of values. So for a bound system like hydrogen atom. So therefore, the solution so is possible only when the possible energy values En are given by En is equal to minus me power 4 divided by 8 epsilon square h square divided by 1 by n square. So this is equation 11, and this equation 11 actually gives the possible energy eigenvalues of the hydrogen atom, where n is another quantum number, and that is what we call it as principal quantum number, and the possible values of n are 1, 2, 3, etc., etc., etc. N cannot be given 0 here, because if n is substituted 0 here, E becomes minus infinity, which is not possible. So therefore, the possible value of principal quantum number n starts from 1, 2, 3, etc., etc. If I substitute n is equal to 1 here in the expression 11, I'm going to get E1, and that actually gives the energy of the hydrogen atom in the ground state. If I substitute n is equal to 2, we are going to get the energy of the electron in the first excited state. If I substitute n is equal to 3, then we are going to get the energy of the hydrogen atom in the second excited state, and so on. So just I would like to mention, this is precisely the same equation which can be derived on the basis of Bohr's theory. So therefore, conclusion, so once we apply Schrodinger's equation to the hydrogen atom, we are going to get a solution for energy eigenvalues, and those values, those solutions match exactly with those derived on the basis of Bohr's theory of hydrogen atom. So this is what the thing, and therefore equation 11 actually represents so energy eigenvalues of hydrogen atom. And this expression, once again, I would like to mention, resembles with the equation that is derived on the basis of Bohr's theory of hydrogen atom. I have already mentioned this. The negative value signifies that the electron is bound to the nucleus of the hydrogen atom. Clearly, so the equation is same as the equation derived by Bohr's theory of an atom. I've already mentioned energy should be negative. If energy is negative, then only so it actually corresponds to a bound state called hydrogen atom. Hydrogen atom is an example for bound state. Electron is bound to the nucleus, the proton. It is not actually so escaping from the influence of the proton. So it is actually bound to the electron. Proton are bound to the hydrogen atom. So therefore, such bound systems can have only negative set of values. These negative set of values, energy values, are actually given by this particular expression, equation 11, and equation 11 actually corresponds to energy eigenvalues of hydrogen atom. So this is what. So another important equation that we have are able to obtain, not derive actually. So we are able to obtain on the basis of applying the Schrodinger's equation to the hydrogen atom. Let us discuss your continued discussion. So we have not only equation 10, we have another equation, equation 9. So equation 9 also to be solved. If we solve the equation 9, then so we are going to get so an expression for theta. So this equation 9 is what we call it as polar equation, because the angle theta is what we call it as polar angle. So therefore, the equation 9 is what we call it as polar equation. And once we obtain the solutions, so we are going to get a set of polynomials, and these set of polynomials are called associated Legendre polynomials. Just like in the previous case, solution of equation 10 are actually called associated Laguerre polynomials. In a similar manner, the solution of equation 9, this is polar equation. Equation 9 is polar equation, equation 10 is radial equation. So the solution of equation 10 is what we call it as associated Legendre polynomials. And these associated Legendre polynomials are given by P, L, M, L of cos theta. So Legendre polynomials are functions of not theta, they are actually functions of cos of theta. And these associated Legendre polynomials, they are also decided by two quantum numbers L and M. L is orbital quantum number and ML is magnetic orbital quantum number. So therefore, so the complete wave function of the hydrogen atom is given by psi, so which is a function of N, L, M, L. Now the wave function of the hydrogen atom is decided by three quantum numbers N, L, M, L. N is principal quantum number, so it can take the possible values of 1, 2, 3, and we have L, which is called orbital quantum number, which can take the possible values of 0, 1, 2, 3, etc., etc., etc. And we have another third quantum number Mn, which is called magnetic orbital quantum number. And the possible values of magnetic orbital quantum number are either 0, plus or minus 1, plus or minus 2, etc., etc., etc. So therefore, we can say that the complete wave function of the hydrogen atom, so which are functions of r, theta, and phi spherical polar coordinates. So they are also dependent on three important quantum numbers: principal quantum number N, orbital quantum number L, and magnetic orbital quantum number M. Now they are simply given by the product of three functions: capital R of R, theta of theta, capital theta of small theta, capital phi of phi. So once we write, I've already told, so R of R is actually given by associated Laguerre polynomials, and they are written by R into N. Solution of theta, they are actually called associated Legendre polynomials, and they are actually represented by P, L, M, L of cos theta. So therefore we have P, L, M, L into cos theta. And solution of phi, I have already mentioned. So solution of phi is given by equation 7 here, A into exponential I times ml into phi. So therefore we have another function E into exponential I into ml of phi, where C is some factor. So there are several other factors which come into picture, which I have not mentioned here, but I have taken all those factors into one common factor, and that one common factor I call it as C. And this is not only a common factor, C includes one more thing, that is what we call it as normalization constant also. So therefore, combining all other factors, leaving aside our associated Laguerre polynomials, associated Legendre polynomials, and exponential IML phi, the remaining factors are all combined together in this C, some factor, which is consisting of other factors as well as the normalization constant also. Basically, the wave function psi of N, L, M, L, which is a function of r theta phi, must be a normalized wave function. It is possible to normalize, and that normalization factor is included in this factor C also. I'm not mentioning all those things in detail. So therefore, we can say that the complete wave function of the hydrogen atom is specified by three quantum numbers N, L, M. As I mentioned earlier, wave function of the hydrogen atom actually decided by three quantum numbers: orbital quantum number principal quantum number N, orbital quantum number L, and magnetic orbital quantum number M. Out of which the principal quantum number N denotes the shell or the orbit in which the electron is moving. So for example, if the electron is in N is equal to 1 state, it is called first shell or first orbit. If the electron in N is equal to 2 state, then it is called as second shell or the third shell. Then we have the orbital quantum number L, denotes the subshell or the orbital of the electron. I have already mentioned L is equal to 0 actually corresponds to S orbital. So L is equal to 1 actually corresponds to P orbital, and so on. Similarly, we have one more quantum number ML that actually denotes the orientation of magnetic quantum number. Not rather a quantum number, magnetic orbital angular momentum with respect to some reference direction, which I'm not going to discuss here. So because of which we have another quantum number, that's what we call it as Cnn. Although the wave function of hydrogen atom depends upon the other three quantum numbers, the energy of the electron only depends on the principal quantum number n. Wave function is decided by three quantum numbers n, l, and ml. But if I go to my previous slide, I can see that we can see that the energy value of the hydrogen atom is not decided by L and ml. It is purely decided by the principal quantum number n. So therefore, energy of the electron is a function of principal quantum number n, not on. It does not depend on arbital quantum number L and magnetic orbital quantum number ml. So as per syllabus, we need to mention the ground state wave function of the hydrogen atom. If you go for the ground state, n is equal to 1 actually corresponds to ground state. So if I substitute n is equal to 1, then the possible values of L can actually take n different set of values starting from 0 to n minus 1. If I go for n is equal to 1, then there is only one possibility, that is L is equal to 0. And if L is equal to 0, the possible values of ml is minus L to plus L. So there is minus 0 to plus 0 including 0. So therefore there is only one possible value of ml, that is ml is equal to 0. So therefore we can say that the ground state of hydrogen atom actually corresponds to n is equal to 1, L is equal to 0, and ml is equal to 0. We substitute all these values in the equation 12, and if you do the simplification, which I have not done here, I have mentioned it directly here. So we are going to get the ground state wave function of the hydrogen atom. The ground state wave function of the hydrogen atom, n is 1, L is 0, ml is 0. So therefore it is psi 100. Psi 100 represents the value of wave function of the hydrogen atom in the ground state, because n is equal to 1, L is equal to 0, and ml is equal to 0 represents the ground state. So therefore we can write it as r of 10. So phi of 00 and theta of 00 and phi of 0, along with some normalization constant. And totally we can write that one as 1 by square root of 2 by 1 by square root of 2 divided by a naught to the power of 3 by 2, and exponential minus r divided by a naught, where r is the radial coordinate r. And we have introduced another constant a naught here, and the a naught is what we call it as Bohr radius. And so the Bohr radius has a value of 0.53 angstrom. It is actually the expectation value of the radius of the electron in the ground state of the hydrogen atom. Classically, we call it as the radius of the first Bohr orbit of the hydrogen atom. But as per quantum mechanics, there is no definite trajectory. So therefore, there is no orbit in the case of hydrogen atom. There is only orbital. So therefore, we talk of expectation value of the the distance of the electron or the radius of the electron, rather than the radius of the electron, the expectation value of the hydrogen atom. So in the ground state for the distance, and it is what we call it as Bohr radius. And the value of Bohr radius is given by 0.53 angstrom. So this is what about hydrogen atom. We are able to discuss. So application of the Schrodinger equation to the hydrogen atom. Of course, very basically we have not touched upon the mathematics completely, but even without touching the mathematics, so we are able to write down the expression for the energy eigenvalue of hydrogen atom, and we are also able to write the expression for the ground state wave function of the hydrogen atom. So this is as per the syllabus. I am stopping my discussion here. We shall continue our discussion in the next session. Thank you.